Hello students, today we are going to start a new chapter, that is thermodynamics. In this chapter, first of all we will learn what is the thermal equilibrium when the bodies or the systems are said to be in equilibrium. Then we will learn the Zeroth Law of Thermodynamics, which tells us about the equilibrium bodies. Then we will learn about the heat, internal energy and the work related to the thermodynamic systems. Now we will see the various graphs. In that we will see various PV graphs, VT graphs, PT graphs for different thermodynamic processes. After that we will see the first law of thermodynamics, that is based on the conservation of energy. Then we will see the specific heat capacity of water. In that we will prove that famous relation Cp minus Cv is equals to R. Then we will understand what are the thermodynamic state variables and the state equation. After that we will see the thermodynamic processes, the isothermal process, adiabatic, isochoric, polytropic, isobaric processes and work done in these processes. Then we will see the heat engines, the application of thermodynamic processes as a heat engine and refrigerators and heat pumps. After that we will see the second law of thermodynamics. Then the reversible and irreversible processes, and at last we will see the Carnot engine and some previous year examples. So let us begin. Now let us understand about the thermal equilibrium. In mechanics, the equilibrium means that there is no net external force acting or torque acting on the system. But in thermodynamics, the term equilibrium is quite different. To understand the term thermodynamic equilibrium, let us first take few examples. When hot water is mixed with cold water, the final temperature of mixture is somewhere between the initial of hot and cold temperatures. Similarly, when a cube of ice is dropped in a hot tea, the ice melts and the temperature of the tea decreases. In both of these examples, when the temperature of the mixture becomes almost stable with the surrounding, there is no further exchange of energy. In general, whether or not a system is in state of equilibrium depends on the surroundings and the nature of the wall that separates the surrounding system from the given system. Now let us consider two systems, A and B, which are separated by an insulating wall. A wall, insulating wall means a wall that does not allow the flow of energy, is known as adiabatic wall. So let's say this is adiabatic wall. Now, these systems are insulated from rest of the surroundings by adiabatic walls. A thermometer is used to measure the temperature of A and B and are different initially. Now, the adiabatic wall between A and B is replaced by a conducting wall. Let's see, this is conducting wall. This conducting wall that allows the energy to flow from one to another is also known as the diathermic wall. Now, the thermometer records the same temperature for both the system. This concludes that there is no further exchange of heat between them. This state in thermodynamics is called thermal equilibrium. So, we may say that in thermal equilibrium, the temperatures of the two systems are equal. Now, we have seen that through adiabatic wall, heat cannot be transferred, while through conducting wall, heat can be transferred easily. To understand what Zeroth Law of Thermodynamics actually states, let us imagine a situation where two systems A and B are separated by an adiabatic wall. While both of the systems are further in contact with a third system C by conducting wall. This is adiabatic wall and this is conducting wall. Now, the states of the system will change until both system A and B come in thermal equilibrium with third system C. After the thermal equilibrium is achieved, if the adiabatic wall between A and B is replaced by the conducting wall and the conducting wall between A, B and C is replaced by the adiabatic wall, it is found that there is no further change in the states of the system A and B. In simple language, we may say that when any two systems are in thermal equilibrium with each other, there must be a physical quantity that has the same value for both. This physical quantity, whose value is equal for both the system in thermal equilibrium, is called temperature. Thus, when two bodies are in thermal equilibrium, their temperatures are equal. So, the system in thermal equilibrium must have same temperature. This is necessary condition for systems to be in thermal equilibrium. This experimental facts is concluded in Zeroth Law of Thermodynamics, which states that if two systems are in equilibrium with a third system separately, then they are in thermal equilibrium with each other. If two or more systems are said to be in thermal equilibrium if there is no exchange of heat between them when they are brought in thermal contact. Now, let us understand the concept of heat, internal energy, and work. The concept of the temperature arises from Zeroth Law of Thermodynamics. Temperature determines the direction of flow of heat when two bodies are placed in thermal contact. Heat is that form of energy which gets transferred between a system and its surrounding because of temperature difference between them only. Heat flows from the body at higher temperature to the body at lower temperature. The flow stops when the temperature equalizes, i.e., the two bodies are in thermal equilibrium. Now, let us study the concept of internal energy and work. Internal energy. It is the sum of molecular kinetic energies and potential energies. In the frame of reference relative to which the center of mass of the system is at rest. That means there is no external force acting on the system. It is called the internal energy of the system. The internal energy is denoted by U. U depends only on the state of the system. So we can say it is the state variable. It is independent of path taken to arrive at that state. If we neglect the small intermolecular forces in gas, the internal energy of the gas is just the sum of kinetic energies associated with various random motions of its molecule. So, if we ignore the intermolecular forces, there will not be any potential energy of the system. The internal energy of a system does not depend on the motion of a system as a whole. That is, the sum of kinetic energy of only the constituent molecules due to their randomness inside the system is considered. Now the work done. When piston of a cylinder is pushed down or pushed up, the work is done on or by the gas. The work done is denoted by W, and it is the integration of P dV that we can write work done is equals to P delta V. Now, let us see some sign convention rules for heat, internal energy, and the work done. The heat delta Q. If heat is supplied to the system, then delta Q is taken positive, and if heat is released by the system, then delta Q is taken negative. Now, the internal energy, delta U. If temperature of the system is increased, then delta U is taken positive, and if temperature of the system is decreased, then delta U is taken negative. Now the work done. In this whole chapter, we will consider all the thermodynamic processes, considering the heat engine at the back of our mind. We can say heat engine is like an engine of bike or car. If car or bike moves due to the internal combustion of fuels and it moves automatically, then we can say it is the work done by the system, and that is what we require from the heat engine. So, if the system does the work, then it is positive. But if we have to do the work on the system, then it is negative. So in this case, we will take the work done positive if work is done by the system. Then work done is taken positive. And if work is done on the system, that is, we have to push the vehicle to move it. It is the example of work done on the system. Then it is taken negative. These are the sign conventions which we will follow throughout the chapter. Now let us see some various graphs on PV, VT and PT graphs. Now let us see various graphs. First, we will start with various PV graphs. In the PV graph, on the y-axis, we will represent pressure, and on the x-axis, we will represent volume. Now, if we take a point, then this point represents certain pressure and certain volume. So, the point represents the state of a gas. So, state of gas is shown by the point, single point. Now, if we draw a line or a curve, let's say we have drawn a line from point 1 to point 2, then this line shows a process. So, line or curve shows a process on PV diagram. If we see from 1 to 2, the pressure remains constant. So this is isobaric process. In this line, the volume remains constant, pressure is decreasing, but the volume remains constant. So it is isochoric process. The process from 1 to 3. In the PV diagram, it is isothermal process. And the process from 1 to 4, it is the adiabatic process. Any slow process is isothermal process. And any fast process is adiabatic process. So, if in the question it is not mentioned directly that process is whether isothermal or adiabatic, but if it is mentioned that the process is a slow process, then we can understand then that it is the isothermal process. And if it is mentioned that the process is fast process, then it is understood that the process is adiabatic process. In all this process from 1 to 2, 1 to 3 or 1 to 4, we can see that the volume is increasing from 1 to 2, from 1 to 3 or from 1 to 4. The volume is increasing. So This is the PV graph for various processes for expansion. We can also draw the graph for compression. So let us see the graph for compression. PV. This process from 1 to 2. All the process will be denoted same. This 1 to 2, 1 to 3, 1 to 4 and 1 to 5. This will be the isothermal. This will be pressure remains constant, so isobaric. This is isothermal 1 to 3. 1 to 4 is adiabatic and 1 to 5 is isochoric. And this is the PV graph for compression. From this we can say that all the graphs or all the curves are plotted for single equation. And different values. That single equation is PV power n is equals to constant. If n is equals to 0, then we can say P is equals to constant. Then it will be the adiabatic process. If n is equals to 1, then PV is equals to constant. Then it will be the isothermal process. For the different values of gamma, we will have the adiabatic process. And if n is equals to infinity, then volume will be constant, then it will be isochoric process. So all the graphs are plotted for the single equation, that is PV power n is equals to constant, and for the different values of n. Now let us plot the isothermal and adiabatic processes. An adiabatic process for monoatomic, diatomic and triatomic linear. The PV graph. We know the basic equation is PV power n is equals to constant. For n is equals to 1, it is isothermal process. And for n is equals to gamma, that is PV power gamma is equals to constant, it is adiabatic process. For monoatomic, the value of gamma is Cp by Cv, that is 5 by 3, that is 1.66. For diatomic, gamma is equals to 7 by 5, that is 1.4. And for triatomic, gamma is 4 by 3, that is 1.33. So let us plot the graph for expansion. this will be n is equals to 1. Then gradually the value of n will increase. So n is equals to 1.33, n is equals to 1.4, and n is equals to 1.66. This is isothermal. This is for triatomic. This is for diatomic. And this is for monoatomic. From this we can see, as we move downward, the atomicity of the gas keeps on decreasing. Now we have drawn this graph for expansion. As the volume is increasing, this is the graph for expansion. Now, if we draw the same graph for compression, and this will be the isothermal. This will be the value of n is equals to 1. This will be 1.33, 1.4 and 1.66. So this is isothermal graph. This is for triatomic, for diatomic and for monoatomic. This graph shows the compression as the volume is decreasing. So in the compression graph, if we move upwards, then the atomicity of the gas will decrease. Now let us see the first law of thermodynamics. The first law of thermodynamics is in accordance with the law of conservation of energy. According to the Clausius statement of first law of thermodynamics, the heat given to the system is delta Q is equals to delta U plus delta W. Here delta Q is the heat supplied to or absorbed by the system, delta U is the change in internal energy, and delta W is the work done. In the differential form, we can write dQ is equals to du plus dW. We should note that the units of dQ, du and dW should be same while using this equation. We have seen the sign convention that if the temperature of ideal gas increases, then du is taken positive, and if the temperature decreases, then du is taken negative. If heat is given to the system, then the dq is taken positive, and heat is taken out from the system, then dq is taken negative. dW, that is volume of the system increases, that is work done by the system, then dW is positive, and if work is done on the system, that is volume is decreasing, then dW is taken negative. If volume is constant, then dW will be 0. The dQ and dW depend not only on the initial and final states but also the path or the process. So they are the process dependent variables. But the change in internal energy depends only on the initial and final energy of the system or initial and final states of the system. So du is state variable. For all processes, du is taken as NCV delta T. How? We will see it further. Even when volume is not constant, du is taken NCV delta T only. During melting, change in volume is neglected. Therefore, delta W is 0, then delta Q is equals to delta U. But during boiling, the change in volume is not 0. So, dQ will be equal to du plus P delta V. This is during boiling, and this will be greater than the du. Now let us see one example based on the first law of thermodynamics. In this example, find the internal energy if heat supplied to the system is 50 joule. If heat is supplied to the system, then delta Q will be positive, that is 50 joule. And work done by the system is 16 joule. Here work is done by the system, then it will also be positive. The first law is delta Q is equals to delta U plus delta W. So delta U is equals to delta Q minus delta W. So 50 minus 16. So delta U will be equal to 34 joule. As delta U is positive, the temperature of system will increase. Now let us see how we can find work done from the PV diagram. The area under PV diagram or PV graph will be the work done. As the area under PV graph gives the work done, it is also called the indicator diagram. Now, in the given PV diagram, we are moving from state 1 to state 2. Now, in this process, if we want to find the work done, then we will consider the area under the graph. The area is taken below the curve and above the volume axis. So this area will give us the work done. Here, from 1 to 2, as the volume is increasing, it is the expansion process. The expansion process, that means the gas in the cylinder is expanding and the piston is coming out. That means work is done by the system and so the work done is taken positive. So for expansion process, work done is taken positive. Now in the reverse case, from 1 to 2, again area under the graph will give us the value of work done, but here it is the compression process because volume is decreasing and moving from here to here. So it is the compression process. That means we have pushed the cylinder, due to that the volume of gas, we have pushed the piston, due to that the volume of gas in cylinder is decreased. So work done on the system, so delta W will be negative. Now these are the open processes. This both are open processes, but all the practical processes are cyclic process. So let us see how we can find the value of work done in cyclic process. The meaning of cyclic process is the initial state is achieved again. For example, this is a cyclic process. So area under this graph will give us the work done. Now, if the cyclic process is clockwise, then the work done is taken positive, and if the cyclic process is anti-clockwise, then work done is taken negative. So for clockwise it is positive, and for anti-clockwise the work done is negative. Now let us see one example. We are given a PV graph. Let's say it is like this. Starting from this point 1, 2 and 3. The pressure at this point is P1, pressure at this point is P2, the volume is V1, and here volume is V2. We want to find the work done. The work done will be the area under the triangle, but as the cyclic process is clockwise, it is taken clockwise, so the work done will be positive. So work done will be positive. So delta W will be equal to half into base into height. Base is V2 minus V1 and height is P1 minus P2. So this will be the work done in the process. Let us see the another example. A PV graph is given for the process from A to B. This is the process of expansion. We have to comment on the work done. Now, one can say that the work done is decreasing and then it is increasing. As the graph is going down and then it is going up, one can say that work is decreasing and then it is increasing. But it is not true. If we start from this point and we divide this whole area into small strips, then constantly as we move from A to B, we are adding the area. Area is always added. So work done is increasing constantly. It is increasing always from A to B. But the rate of adding work done is decreasing because here the area was more, gradually area is decreasing. After this point again the area is increasing, so work done is increasing. So the rate of doing work is first decreasing and then it is increasing. Here remember, work is always added, so work is not decreasing or increasing. The rate of doing work is first decreasing and then increasing. Now let us compare the work done in adiabatic and isothermal processes. First we will see the expansion process and then we will see the compression process. So first of all, let us draw the graph. The PV graph. This is the isothermal process and this is the adiabatic process. We are taking initial and final states to be same. This 1 to 2 is isothermal process and this 1 to 3 is any adiabatic process. This is the process of expansion. Here clearly from this graph we can say that the area under isothermal is more than the area under the adiabatic process. So work done in isothermal expansion is greater than the work done in adiabatic. Now let us see what happens in the compression. This is the isothermal graph and this is the adiabatic curve. We are considering the same states of pressure and volume. Here in this graph we can see the area under the isothermal is less than the area under the adiabatic curve. So work done in isothermal compression is less than the work done in adiabatic compression. So which work done is more? It will depend on whether it is expansion or compression. If it is the expansion, then work done in isothermal is more, and if it is compression, then work done in adiabatic is more. In this example, a PV graph for cyclic process ABCD is given. We want to find the work done in process AB, in process BC, in process CD, and in process DA, first separately, and then we want to find the work done in whole cyclic process ABCDE. So first let us start the work done in process AB. The work done is P delta V. So we can write pressure from A to B is constant, that is 12 into 10 power 5 Pascal, and delta V is 6 liter minus 1 liter, that is 5 liter, converting it into meter cube, 5 into 10 power minus 3. So this will give us 660 into 10 power 2, that will be 6000 joule. Now work done in BC. Work done is P delta V. For B to C process, the volume is constant, that is 6 liter. So work done in BC process will be 0. Now work done in CD process, that will again be equal to P delta V. The pressure is 2 into 10 power 5 Pascal, and the change in volume is 1 minus 6 into 10 power minus 3. So 2 into 10 power 5 into 5 into 10 power minus 3. So that will be 10 into 100, that is equals to 1000 joule, but it will be negative as it is the compression. The work is done on the system. The work done in process D to A or A to D is P delta V. Again, from D to A, volume remains constant. So the work done in this process will be 0. Now work done in whole cyclic process ABCDA will be equal to the area under the curve. So we will take the area of this rectangle. Now as the process is clockwise, the work done will be positive. So the area under the curve will be equal to (6 minus 1 into 10 power minus 3 into 12 minus 2 into 10 power 5. So this is 5 into 10 power minus 3 into 10 into 10 power 5. So there will be 50 into 10 power 2. So this will give us the answer 5000 joule. So this is the total work done in whole cyclic process. Now let us compare the temperature on a same scale for various isothermal graphs. This is PV diagram. We have drawn various curves for different isothermal process. If this is temperature 1, temperature 2, temperature 3. If this is for 300 Kelvin, then T2 can be 400 Kelvin, T3 can be 500 Kelvin. So from this we can see that as we move up in the isothermal processes or as we move up in the PV diagram, the temperature will increase. From this we can compare the various processes and the temperature at given particular state. For example, a cyclic process is given A, B, C, D. We want to compare the temperatures. We have to comment on the temperatures from A to B, B to C, C to D and D to A. To compare this, we can imagine some isothermal curves in the background. So as we move from A to B, we are moving up in the PV graph. So from A to B, the temperature is increasing. Now as we move from B to C, we are moving down in the PV graph. So the temperature will be decreasing. As we move from C to D, again we are moving down in the graph. So again, in this case it is decreasing. The temperature is decreasing. And as we move D to A, we are moving up in the PV graph. So from D to A, again the temperature is increasing. In this way, we can imagine the isothermal lines in the background of given curve, and from that we can compare the temperatures in given processes. Now let us draw the VT diagrams, the volume temperature diagrams. There will be volume on y-axis and temperature on x-axis. If we draw a straight line, 1, 2. From 1 to 2, the volume remains constant, so it is isochoric. As the volume is constant, we cannot classify it as a compression or expansion. If we draw a vertical line, then the temperature will be constant. If we are moving up, then volume is increasing, then it will be the isothermal expansion. And if the arrow is given in downward direction, then it will be the isothermal compression, as the volume is decreasing. Now, if we draw straight lines, then what will be the meaning? We can see the ideal gas equation PV is equals to nRT. From this we can write V by T is equals to nR upon P. So V by T is the slope of VT graph, so we can write slope is directly proportional to 1 upon P, as nR is constant. So the slope of VT graph will give us the pressure. Now, as the slope increases, the pressure will decrease. Let's say there are two diagrams for pressure P1 and P2. As slope for pressure 1 is more, then the pressure 1 will be less, as they are inversely proportional. So from this we can conclude that P1 is less than P2. So from the given VT graph we can conclude this informations. Now let us draw the pressure temperature diagrams. In the pressure temperature diagrams, there will be pressure on y-axis and temperature on x-axis. If we draw a straight line, then the pressure will be constant, so it will be the isobaric process. If we draw a vertical line, then it will be isothermal process. Now, if we are moving up, then pressure is increasing. If pressure is increasing, then volume is decreasing. So it will be the isothermal compression. And if we move down, then pressure is decreasing, volume is increasing. So this will be the isothermal expansion graph. Again, in this graph also we can draw some straight lines having some slope. From the ideal gas equation, PV is equals to nRT. We can write P by T is equals to nR upon V. P by T is the slope of this graph. So we can write slope is inversely proportional to V. So slope will give us the volume. If we have drawn for two different volumes, V1 and V2, then the graph having more slope will have lesser volume. As the slope of V1 is more, then we can write V1 is less than V2.